Morning, everyone. So I'm Andrew, and I'm enterprise software developer, and what I do, I convert JSON to XML. And as it was told before in the introduction, in order to do this, we have a domain-specific language, an interpreter, a compiler to multiple architectures, and everything else which makes our life of functional software developers fun and pleasure. But today, I'm going to talk about some more theoretical questions. And we're going to talk about data structures in Haskell. Just a quick, brief recap. If someone is not familiar with Haskell, Haskell, at least its implementation in Glasgow Haskell compiler, it's a lazy language. So it's as lazy as possible. Every expression will be deferred. Every evaluation will be delayed until its result is unavoidably needed. And Haskell will do its best to be lazy. So for example, in Haskell, we can define infinite data structures. Here on the slide, we define an infinite list of integers. So we just write, OK, GHC give us integer numbers from 0 and to infinity. And then we can write function which will map these integers. And we'll write it in such a way that for 42, it just returns 3, because it's a good number. Everyone knows 42 is an answer to every question. And if it's not 42, so it's not an answer, then just loop forever and do not answer silly questions. And if we map our infinite list with this function, which has infinite loops inside, and take element number 42, Haskell instantly returns us 3, even while this list is integer itself, and even if its elements are diverging computations. So from pragmatic point of view, laziness in Haskell is an abstraction to handle some potentially infinite processes, like generate integers one by one. Yes. Maybe we do not, of course, in practice on our Turing computers, we cannot compute till infinity and back 2 times. In practice, we can just go to some limit. But this is a potentially infinite process. And laziness is a way to treat this process as an actually infinite object in a pure functional way. So I'll give some motivating example. I must confess, this example has no relation to practice, and actually all what I'm going to talk about was written and prepared for some number theory things. But let's proceed with it. So a schedule. A schedule is a set of dates. Maybe it's a schedule of your vacation. Maybe it's a schedule of your company. And we will define many types of schedules. We can either say, OK, this is a universal schedule. Every day, every date is present in it. Yeah, it's like a full set. Or we can define schedule as a literal list of dates. We say, OK, I have vacation. It's 3rd, 2nd, and 4th of May. And that's it, and no other dates at all. Or we can say, for example, you know, my weekend schedule is all Sundays and all Saturdays. And it's also a fine definition of schedule. We can union schedules. For example, if I want to have a schedule of my free days, then I have to merge schedule of Saturdays, schedule of Sundays, and the literal list of my vacations tracked in your enterprise vacation tracking system. Or maybe I need to intersect schedules. For example, I'd like to know what is the schedule of free days for me and for my girlfriend. And yes, in practice, we have all kinds of random stuff and definitions of schedules like, maybe return schedule of each 5th Tuesday of a month, which is preceded by the 4th Monday of a month, and so on. Okay, so this looks like a definition of some data type. How can we model a schedule? A schedule is a set of dates. Oops. So all these operations are just some plain operations on sets. You can union sets, you can intersect, you can difference, and so on. So just some example. For example, you buy Microsoft stock on New York Stock Exchange and Dubai Financial Market and sell it on Moscow Exchange. And you'd like to know what is your trading schedule, how many days you have to come and make your trading. First of all, you compute schedule of New York Stock Exchange. So you first take the full calendar, then you remove all Saturdays and Sundays, then you remove all public holidays in USA. Then you proceed to Dubai, you again take full calendar, you remove all Fridays and Saturdays because Sunday is a working day in Dubai, yeah? And you remove a list of public holidays in Dubai. What are we gonna do with Moscow Exchange? How can we get a schedule of Moscow Stock Exchange? It's a simple number of steps. Any ideas? Yeah, step 1.
Remove Saturdays and Sundays.
Yeah.
And remove public holidays.
Yeah. And one more step. No, just with Moscow. What else? It's kind of unique property of, Moscow, Kiev, Minsk, some other cities in Eastern Europe. We have working weekends. It's when you work on Saturday or Sunday. So you have, yes, as it was said, it's like this funny riddles how to place a giraffe in your refrigerator in 3 steps, and how to place an elephant in your refrigerator in 4 steps. So Moscow is in 4 steps. And yes, of course, finally, we just merge schedules of New York and Dubai and intersect them with schedule of Moscow. In practice, these computations are much, much, much more unwieldy because there are delays, there are things like, okay, give me trading schedule when yesterday Dubai was open and such that today New York is open and tomorrow and 2 days after that Moscow will be open and all kinds of that. What we are not gonna go that deep. So as we told before, yeah, schedule is basically a set of dates. How do you represent a set in Haskell? Let's assume that the values of this type are ordered. You can use finger trees, binary trees, all kinds of, but it's like of higher. What is the simplest way to represent a set?
What about function?
Yeah, it's a good approach. Yes, basically the simplest approach is you just have a single linked lazy list of values. Yeah? It's not a very efficient representation of a set, but it kind of works. Yeah? You can insert values into it just by consing values, by prepending them at the beginning. And you kind of can look up some values into this representation of set. Is it efficient or not? How do you look up a value in a list?
Depends on the list of the operations that you need. If you don't need it, if you need to do all the array lookups and you don't need to do it repeatedly, then it's quite okay. Or if you only iterate over the structure. But in the case if you need to do a random lookup many times, then it's not efficient.
Yeah, that's right. Because basically, if you need to have random access to the list, you end up with traversing it in its full length. Okay, what is the solution if we need to make fast lookups, when we need to check whether some value is present in the set or it's not? Yeah. It's all very clever, but you know, like in textbook, we can basically use just a fixed-sized array. It's just a vector. We will put values into this vector, sort them, yeah, and we have nice check for membership. We have nice lookup. If the size of array is n elements, then how can we check whether something is present in it or not in log n operations? Remember, this is an ordered array. Yes, binary search. But what is the problem with vector? Yes, you cannot grow vector efficiently. If you need to insert a new value in your set, you basically need to allocate a new vector, and it takes like O of n operations. And there is, as you already said, you're a very clever audience, there are many data structures which combine both properties with palatable complexity. You can have some binary search tree, you can have some finger tree. Actually, set in Haskell is finger tree as far as I recall. You can have some hash tables, you can have other, but basically it's kind of tree structure. So it looks like in practice we should use these binary search trees. But the problem is that binary search tree is finite. In order to have it, you need to compute all elements because you need to sort them. And if our set is infinite, we have a problem. So the practical question about schedules is how to generate first, like 100 of dates, for example. Yeah, I'd like to know what are first 100 of dates of my trading schedule. For example, my trading schedule is something very simple. It's just an intersection of two schedules, like schedule of New York Stock Exchange is X, and schedule of Moscow Exchange is Y. How could I get first 100 dates of the intersection? Well, I can't.
Basically, you have to take the dates from the whole list until you have the 100 dates.
Yes, but how can I achieve it? Because basically I can take first 100 dates from New York Stock Exchange and first 100 dates from Moscow Stock Exchange, starting from today, for example. Yeah, I can intersect these sub-schedules and check whether the result contains required number of dates. Is it possible, actually, if I take 100 of dates of both schedules and intersect them, is it possible to get exactly 100 of dates?
Could be, but it's not reliable. You don't have.
What is the only case when I intersect two schedules of lengths 100 and get 100 in intersection? Yes, they need to match exactly. And if they do not match, okay, we can take first 200 schedules of New York and first 200 dates of Moscow schedule, intersect them, and check again. Did we get 100 dates? Maybe, because schedules of New York and Moscow are not so much different, but maybe not. Maybe we are talking about Dubai and, for example, some trading schedule of US Treasury. Then we have to take maybe 400 of days from both schedules and so on. It's inefficient and ugly. It's like not cool. Another idea is, let's proclaim, the doomsday is on 29th of February 2900. And let's just compute all schedules until this doomsday, so we have finite schedules, quite long, but finite, and we can put them into set, and you have this all nice operations. Hopefully our enterprise system will get decommissioned earlier than doomsday, and in any case, who cares? Oh, by the way, is it a real date? Yeah?
What can you get to the earliest dates from both lists and compare them, and get depending on the result of comparison, get one more date from one list or from another list. When there is much, put it into the intersect. When there is not much, through one date away and get from some list. Just in parallel, iterate both sets with different required speeds.
Yeah, kind of. Yeah. So is 29th of February 2900 a real date? Is it a leap year? It's not a leap year. Why it's not a leap year? Yeah, it's quite interesting that in actually Gregorian calendar, this year is not a leap year, because it's divisible by 4, but not divisible by 100. And it's even more interesting that in this year, there are a couple of Orthodox churches, Eastern Orthodox churches, which basically said that we cannot follow the calendar of some Western Pope. We will have our revised calendar, which will match Gregorian calendar up to this date. And on this date, these Orthodox churches will have leap year again. So this is the year when our countries, I mean Belarus, Ukraine, can enjoy 3 Christmas in a year. We can celebrate by Western churches, by Eastern Orthodox churches, and by some Southern Orthodox churches in Africa. So, but this is very huge schedules, it's very inefficient. We'd rather work with infinite sets in lazy fashion. Unfortunately, we cannot do this with trees or with finite-sized arrays. So we are left with only lists. So how to merge ordered lists in lazy fashion? We cannot use operations from data lists. They are not for this kind of thing. Yeah, what we want to achieve, we'd like to have merge, and we have 2 lists, and we'd like to merge them so that the result is a sorted list. And we'd like it to work with infinite lists also. So if I have to merge a list of odd numbers and a list of even numbers, I'll get a list of all numbers at all. It's not difficult to write this function. Yeah, basically, everyone has already written such one when in his some kind of algorithms of sorts 101. It's like a merge sort. Yeah, merge sorted is a thing when you get 2 ordered arrays and combine them in the resulting array of values. You just set pointers at the beginning of the lists, and you compare the values at heads, and if the first list starts with a smaller value, then you output it and merge the tails, and if it's equal or it's less than the head of second list, then you return the head of second list and proceed. You may note that if x is equal to y, we return only y, because we are working with sets. Sets are unique. Sets do not allow repetitions of elements inside. And similar definitions can be given for intersection, difference, and so on. And there are packages which define operations on such sorted lists. Yeah, I found at least 3 of them, and all of them on Hackage, and all of them has the same fatal flow, and also they are kind of abandoned, allow repetition, so it's not true sets, provide no type safety, no type wrappers, and we Haskellers like are proud of our type systems. Oops. So the solution is just write a new package, and I did that. It's containers lazy. It mimics full data set interface, so it's just a drop-in replacement of your usual finite sets. Yeah, but it's type safe. It works with infinite sets, and it works for sets without repetitions, because there are separate packages which work with sets where you can have multiplicity. Okay, this is all good, but we have good union, we have good intersection complexity for these sorted lists. Yeah, it's the same complexity which you can get from binary tree or any other kind of tree, but we kind of have still bad lookups. Because since the underlying structure is a list, the lookup may take n operations where n is the length of your list. Can we get better? We can try to define such semi-lazy structure, which will still represent sets, infinite sets possibly. It will have a strict initial values, which we will keep in binary tree, and we will have a lazy tail, which we will keep in list, in ordered lists. Sometimes we just have some clue, for example, how many values should be required to compute first 100 dates of result. Maybe we can just have some intuitions that it's like, okay, let's compute first 300 of values in strict fashion, and everything else, if we are unlucky, we will keep in lazy list. We will have bad complexity for it, but hopefully we will not traverse that far often. So for example, we can have like head of 4 elements kept in set, and everything else starting from 10, 12, 20, and so on, we will keep an infinite lazy list. And if we operate mostly on the first 10 dates, yeah, we are fine. We just look up into set. Or otherwise, well, we are not that fine. And we need to maintain the invariant that the last element of strict part is less than the first element of lazy part. It's essential invariant because if we messed up it, well, we cannot look up into this structure because we just do not know, should we look up into the strict part or should we look up into tail? For example, if this invariant is maintained, then it's easy to understand in which part of the structure I should look up my values. If it's less than 10, then I go to set, and if it's more than 10, I go to list. It's not quite easy to maintain this invariant. This is the valid definition of merge, actually. It's quite simple thing. A merge should return us union of our structures, and I have a structure which has 2 fields, so I'll just merge first fields respectively and last fields. Is it valid? Yeah. So this implementation of merging doesn't maintain the invariant. For example, you can merge these 2 sets and get some kind of nonsense. Yeah, you have in strict part you will get like 10, and then you have lazy part which starts from 0. So now we have no idea if we'd like to check whether, for example, 9 is present in this set. We have no idea should we look into first part or into second part or in both. But if we have to look in both parts, then we have no benefit over just using lists. So the valid implementation is kind of complicated. Not very much, but kind of. And it appears that to achieve better laziness, we should enrich our data type with a delimiter which will keep the value which is between set part and lazy list part. The implementation are available from my GitHub if someone wants to dig in dirty details. And we are moving further. So we can have lookups in kind of maybe logarithmic time, or if we are unlucky in linear time, but can we achieve some even more impressive result? What is the data structure which we use when we have many lookups, almost no inserts, and for example, we work with something as simple as just integers, even ints. So I have an int set, and I like to check whether something is present in int set or it's not. And let's have a trade-off. Let's assume that we have a lot of memory. We can trade off memory for better speed. Yeah, bit set is a solution. Because basically you just spend 1 bit for each value. If you need to look up whether something is present, whether, for example, n is present in your set, you just go to n's element, to n's bit of your memory chunk, and you just check is this bit set or it's not. If it is, then your value is present, otherwise it's not. And bit arrays provides wonderful intersection and union, because it's just bit operations that are super fast on any modern computer. Okay, on any computer, because all our computers are binary machines, and none of them is lambda calculus machine, unfortunately. There is Haskell implementation of bit arrays in a package called bitwag. And can we have an infinite bit array? Because we'd like to have some infinite data structure, but which will still provide us bit array kind of access in constant time. Since it's infinite, it must somehow involve laziness. We cannot allocate just infinite chunk of memory. So let's kind of get some tricks from imperative languages, from mutable state approach, how you work with, as I told before, this laziness is a way to deal with some potentially infinite processes. And what is the potentially infinite process behind having an infinite array? It's basically a dynamic array. It's an array which can grow in size potentially infinitely large. But at any given step of computations, it's finite. So how do we work with dynamic arrays in imperative languages? Of course, we can just resize and reallocate them each time when you insert. But it's much better just to allocate some space at the end of your array. For example, up to 2 in power k elements. So if you, for example, have 10 elements, you allocate space for 16 elements. When you grow your array, you just put values in your free space. When your dynamic array grows larger than 16 elements, you just allocate 32 elements, and now you can continue growing it up to that value. And this saves us from reallocations each time. And we can translate this trick from mutable state world to a pure functional way of dealing with things almost literally. Let's have a list of bit arrays of growing size. First element of this list will be pointer to just one machine word, just 64 bits. Second element of array will be pointed to twice bigger bit set, and so on. And this list is potentially infinite, and it's lazy list, so we do not have to allocate all these bit arrays at once. So it's the lookup is basically the same. We just need to understand which block corresponds to our index. Yeah, for example, if we want to have element number 200, yeah, it can be found in the first block, it's too small. It can be found in the second block, it's still too small, but it definitely should be present here. Yeah, so it's the 8th bit of this third block. And we can actually use not lazy list, but lazy vector. So we'll have like lazy vector of bit arrays, of growing bit arrays. And it means that we have random access to outer vector in constant time, and then we have random access to inner bit set in constant time. So we finally achieved our holy grail. We get our constant time indexation for our schedules, potentially infinite schedules. It appears that this idea with lazy outer array and growing inner arrays is very fruitful because you can store not bits, but basically any other structure which you would like to. I have written a simple package which implements this approach. Actually, I stole this approach from number theory again. It's very popular in analytic number theory, and it's quite fascinating how this interconnects with very abstract branches of mathematics. And you can have like function tabulate, which will take function, which will take a predicate, for example, and will populate an infinite bit array or infinite array of some other, of some type A. And you can have index function, which will take pointer to this potentially infinite bit array or array of some type A, and it will take index, and it will return value in constant time. So you can use this, for example, for caching. You can just have some expensive computation. You can put it into, you can basically say, okay, this cache will be application of expensive function to an infinite lists of inputs from 0 to infinity. And it's like, okay, here you go, here's your cache. And then you just can index this cache in constant time. So what we get here, we get like purely functional caching for functions from integer indices. And you do not have to specify beforehand what is the largest index. You can also use this approach to deal with recursive functions. Yeah, you can, for example, define Fibonacci numbers in a naive exponential way. Everyone knows it's bad. And you can cache it as is, but it's still bad because, okay, you will save yourself from repeated calls to your array, but you wouldn't save yourself from recursive calls inside a single call. So we can use the usual trick. We can use fixed point combinator. Unfortunately, I don't have much time to stop at it. Yeah, but it's basically a tool which introduces recursion into lambda calculus. It's a very fundamental thing. It appears that you can rewrite our Fibonacci function, which is like wildly recursive. You can rewrite it in non-recursive style. Yes, this function is not recursive, but it's essentially the same Fibonacci function. And you can just add this fixed combinator to retrieve back your Fibonacci function. And this package, Chimera, it provides a handy function tabulate fix, which allows you to cache values of recursive function so that even recursive calls are using your cache. So you can have your Fibonacci numbers in linear time. So summary. we can use combination of strict init and lazy tail to work with infinite sets. If lookups are a bottleneck, we can resort to bit sets, add rate space for speed, and this is a hybrid of lazy array and strict bit array. And the latter approach can be generalized. You can store any data and have a transparent caching of functions, including recursive ones. Thank you.
Okay, Andrzej, thanks for your talk. Does anyone have any questions? One second.
So with the lazy set, if you call a function like size, would it force to normal form the whole set, right?
Yeah, of course, if you try to get size of infinite set, it will just hang indefinitely. It won't be able to recognize that it's actually infinite and return you infinity.
Anyone else? Okay, then thanks, Andrzej. Thanks for your talk. And now I think we have a coffee break for 20 minutes, and let's see you later.